Hey there, all you cool cats and kittens. Welcome back to Bio 107. This week we're going to be covering Module 10. So the subject matter for this week's lecture series is the astronomical context for biological evolution. Basically, that's a fancy name for saying the universe. So we're going to be talking all about stars, galaxies, and how the universe has been formed. So the readings for this week's module can be found in your books on pages 166 through 196. So 30 pages of reading, so make sure you're doing that. So let's go ahead and get started with some of the basics. So this week we have a few things due on Tuesday, April 14th. So if you're joining me today, Monday, April 13th, make sure you get all of this stuff turned in tomorrow by midnight. So the first thing on our list is our Module 9 quiz. Make sure you take that. It's our 10 random questions, due by midnight tomorrow, open book 20 minutes. It's all about taxonomy and systematics, so everything we covered last week in Module 10. We also have our lab number 9 on the communicules due tomorrow on Tuesday, April 14th. So make sure you get your lab number 9 turned in. Please take a photo of your communicules or submit it via Dropbox. If you're having a hard time with the images of the communicules, getting them arranged just so, you can use their identification number to place them on the cladogram or the phylogenetic tree, whichever you guys are doing. And so make sure that you are labeling everything correctly so you can get full credit for that. So make sure you turn in your lab. Also due tomorrow is the Evolving Switches video and quiz. So this is a 15-minute video all about stickleback fish. There's 9 quiz questions to be submitted on our Cobra. There are 9 fill-in-the-blank questions, so make sure that you're giving yourself enough time to write in all those answers. And when you submit it, it will say 0 out of 9 or 10 or whatever when you first submit it, but that's just because I haven't gotten around to grading it yet. And then lastly, this is the first you should be hearing about the due date of your presentation. So your presentations are going to be due April 21st. So you're going to be recording your presentation on your topic of choice. If you haven't selected a topic, please do so as soon as possible because we really want to get all of that squared away before you guys start working on your presentation. And I'm going to be talking a little bit about what I expect from your presentation as well today. So there'll be enough time for that. So I'm going to give you guys some new assignments. So due approximately a week from today, you're going to have your Module 10 quiz. That is going to be due on Tuesday, April 21st by midnight. This is going to be all of the quiz questions about Module 10, so what we're covering this week on the universe. So make sure you are taking those quizzes in enough time. Also, there's a universe video that I'm going to be assigning tomorrow for lab. It's about 30 or 40 minutes long. It's basically a planetarium visit, but it's virtual. So originally for our lab this week, we were supposed to go to the Starkle Planetarium on the Parkland campus. However, due to the circumstances we're currently facing, that is not a possibility. And it's difficult to get them to do like a virtual planetarium tour and watch a planetarium video. So what we're doing instead is we have a planetarium video. It's filmed it's used for a planetarium, and you guys can watch that. And I have provided a link to that video in your email address and also on the Parkland website under announcements. So, and if you're having a hard time finding that, just reach out to me and we can make that work. Also, this week I'm giving you guys the assignment to work on your PowerPoint presentations. They are going to be due a week from tomorrow. Tomorrow's April 14th, so they're due 1 week from then. So we're going to be talking about some guidelines really quick here at the beginning of class. Also, this isn't on the PowerPoint presentation, but I just wanted to let you all know that if you're interested in attending my office hours, I am holding virtual office hours, so you'll get to see me via webcam, but I'll be in a Zoom meeting. So I've provided the Zoom meeting website for you guys to click on. There's no password required, so as long as you have a Zoom account, you should be able to click on the link and join in on my Zoom virtual office hours. And if you have questions with any of the labs or the presentation, tomorrow, Tuesday, April 14th, from 11 a.m. to 12 noon is when I'm holding my office hours. So you should all be aware. That's going to be recurring every week until finals. So just drop in, say hi if you want to, or ask a question. And if you don't feel comfortable meeting with me on Zoom, you can always feel free to send me an email. I've been pretty good about answering emails and being in contact with everybody. So I'm around, and just let me know if you have questions. Okay, so for the PowerPoint presentation that you guys have to prepare for me, it is due April 21st by midnight, so you have until midnight to get that submitted to me. Your presentation needs to be 3 to 5 minutes long on your selected topic. I've been responding to discussion threads on people who have posted their topic. There have been a few that were very, very similar. I figure since most of you aren't going to be seeing well, I guess you won't be seeing other presentations and it'll just be me, it's acceptable, so that way nobody else is sitting through the same subject matter over and over again. So those similar presentations I have accepted, so that's going to be okay. So for submitting your presentation, you have several options. So the first option is you can record yourself giving the presentation with a smartphone or a computer webcam, and you can either upload it to Dropbox or put it on YouTube and give me the link. If you're having issues with Dropbox on Cobra, I can provide you with a Dropbox receptacle to drop your presentation in. Since it's only 3 to 5 minutes, it shouldn't be that large, so that's a plus. Another option is you can give me your presentation on Zoom in one of my Zoom meetings. I can make a private meeting, and if you have a webcam or if you don't have a webcam, that would work too. I could share your screen, check out your PowerPoint presentation, and then you can feel free to give me the presentation. If you don't have a webcam, it will still work. I won't be able to see your face if you don't have a webcam, but that's fine as long as I can hear you give the presentation. Another option, so this might work better if you're out in the country and you don't have broadband or high-speed Wi-Fi. You can send me your PowerPoint presentation in advance and then give me the presentation over the phone live, so that's another option. If you have other ideas on how to deliver the presentation for me, please reach out. I did have a student mention and test with me for their PowerPoint presentation, and it seemed to work really nice. There is an option, number 5 here above, to record the presentation on PowerPoint. There's an option for you to record your voice over the slides, and it seemed to work really nicely. And so as long as you have Microsoft PowerPoint, you should be able, and some sort of microphone, you should be able to do that. Okay, so here is going to be the grading rubric that I'm going to be grading your PowerPoint presentations on. And I'll go over this in greater detail during my lab recording that I've uploaded onto the YouTube channel here. There's 3 main categories I'm grading your presentation on. The first is your PowerPoint presentation itself, just the actual PowerPoint. The second thing is your verbal presentation. How good are you presenting the information to me? And then lastly is your PowerPoint sources. So you will have to do a little bit of research and make sure you keep track of the sources that you're using. You do need a maximum of 5. You need to include a works cited slide and then cite them correctly using either CSE or MLA format. So these are just some categories that I'm using to grade the presentation itself. So be sure to go ahead and look through this. I've also included a copy of this rubric in your emails that I've sent you. Also, it's on Cobra under the announcements, and it's under our presentation module in Cobra as well. So this is for you guys to look over and make sure you're checking off all the boxes so you guys can get full credit. But again, I'll go over this better in the lab presentation that I've prepared for you on YouTube. So just keep these things in mind, and don't be tardy in submitting your presentation. You guys have a full week to do a 3 to 5 minute presentation, and it's going to take the place of your lab for this week. So this is going to be essentially your lab assignment. So make sure you're doing this, and hopefully you guys have a little bit of fun doing some of the really cool presentations that you've already selected. So all right, so let's get started with this week's topic. So for Module 10, like I mentioned, the readings are on 166 to 195. There's really 2 portions in your book for this particular module. The first few pages is the origin of the universe. So it's a longer reading, not really any figures or photos, and a few pages long. So that's just text for you to read. And we will go over this probably on the last part of this module. But the rest of the sections here, the 6 sections that we have, we're going to be starting with those, which is more of your standard reading, how we've been looking at in the past modules. So a couple different sections here today. The night sky, we have the origin of stars, brightness of stars, star temperature, star types, and the life of a star. So we're only going to be going over the first 4 sections today. Now the sections are pretty short, sweet and simple. So that's why we're covering so many today. Hopefully I don't go over my time, but we'll see what happens here. Okay, so let's go ahead and get started. So we're talking about the universe, or the astronomical basis of our evolution, how we've been talking about stuff that's been happening here on Earth, but the universe is the bigger picture on what has happened in the past. So if we start at the very, very basic, everybody's familiar with the night sky, right? You've seen the sun, you've seen the moon, you've seen the stars. But watching all of the sun, the moon, and the stars has really helped ancient peoples determine when to plant and harvest crops. So the first people that have occupied areas of Earth really used the night sky for this particular purpose. And even Stonehenge, one of the most famous pillars that exist, those were positioned particularly so that they can help humans follow the movement of the sun and the moon to correspond with the seasons of the year, just to help folks know when to plant and harvest their crops, because eating is a huge deal here, and that's one of the reasons humans have made it as far as we have with the domestication and the planting and harvesting of those crops, in addition to hunting. But this is the primary benefit that humans have gleaned from watching the stars in the night sky. Now there's other things that humans have used stars and the stars and the moon and the sun for as well, such as navigation for folks that were on the early ships. But primarily, it's important to remember that crop harvesting was one of the most important things that we used the night sky for. So if you've ever been familiar with different types of stars, some of you may have been familiar with different constellations that are up in space here when you're looking up at the night sky at night. So a lot of you are probably very familiar with the North Star, otherwise known as Polaris, and that can be found using the Big Dipper. So if you've ever seen the Big Dipper, the edge of the cup for Big Dipper goes straight over to the North Star. So you can see that dotted line kind of pointing to the North Star from that edge of the cup of the Big Dipper. We also have Cassiopeia, which is based off of one of the Greek goddesses here, her constellation, the center of her constellation, also points to the North Star. So you can find the Polaris, the North Star, by using Cassiopeia and the Big Dipper. If you're still having problems finding the North Star, then you can also use the handle of the Little Dipper in order to find that as well. And so the handle of that Little Dipper points over up into the North Star, and that's where all three of those constellations, if you are drawing straight lines from those edges of those constellations, they all meet where that North Star is. And the North Star is really important because it sits directly above the North Pole, and it moves very little over the course of the night. It does move a very slight amount because Earth's rotating on an axis, but it's for the most part very close to where it stays all night long. Okay, so more on the night sky here. So stars do appear obviously as sources of light when you're looking at them, but they generate their own light. So the light is coming from the stars themselves, right? So they're not a reflection or something else that's shining off of something. They are providing their own light. Now we know that our sun is a star, and it is a massive, very dense ball of gases. And the energy that comes off of our sun is released via fusion reactions. And so that is where that energy is coming from to help plants grow and to bring life onto Earth. And all of that energy is then converted on Earth's surface. So that sun, our sun, is providing its own energy, and then thus, therefore, other organisms are using that energy. So this is an image here too. So if you guys watch the planetarium video, this is kind of how the planetarium video will show up. It'll be more of like a full circle in the video on the YouTube, but it will look kind of like this. So it might look a little weird with the edges missing, but it's just because the planetarium video is supposed to be projected on more of a dome shape in the planetarium, but this is the best we have. So. Okay, so you know that you're looking at a lot of different stars in the sky when you look up at night, and they all pretty much look like they're the same distance away. So how far away is a star from Earth? Well, when you're looking at them, they all kind of appear like little specks in the sky, right? You might think that they're all close to the same distance away when you look up in the sky, but that's not always true. All of the stars are various light years away from Earth's surface. So a light year is basically a unit of astronomical distance that uses time. So we're using this distance and time to kind of determine how far away a star or the sun or whatever is from Earth. So if you're looking at the distance from our sun to Earth, it's about 150 million kilometers away. But how far is a light year? Like, what is that measurement? So the light year measurement that we're dealing with here is about 9.5 trillion kilometers. Now, if you're not using metric distance here, it's basically about 6 trillion miles away. So when we're looking at a specific star, that could be, if you have 1 light year away, then it's about 6 trillion miles away. And a light year is it's the distance that light will travel in a year. So that's how long it would take for that amount of distance to travel in 1 year. Okay, so when we talk about stars, they have to come from somewhere. So what is the origin of our stars here? Well, stars are born, if you've seen the movie, from swirling clouds of hydrogen gas. So basically they're starting off as a gas, right? Between stars, between other stars deep in space. So you have this hydrogen gas floating around between other stars in space. And there's gravitational attraction that's happening, and this is mutual. That's this mutual attraction that's pulling these atoms together to form a tight cluster. And we'll talk more about atoms, protons, neutrons, and electrons when we talk about the origin of the universe and the Big Bang. So we have this attraction pulling all of these atoms together in a cluster, and then they're going to form some nebulae. So a nebula is the swirling interstellar clouds from which a star is born. So it's the swirling gases and clouds that are happening between stars from which these stars are being created here. So a protostar is an accumulation of gases that will eventually become a star. So you've heard of the word prototype, right? So the original maybe model of something that will be put into production. So you maybe have a prototype of a shoe, and you're looking at it to try to determine what's the most aerodynamic way. Well, it's basically the original or the first version. A protostar is like a rudimentary formation of a star. So when you hear the term protostar, it's what is going to become that star in the end. And stars really have three main components when we're looking at what a star is made of. So if you're looking at the interior of a star, the inside of our star includes three different sections here. The first section is going to be the core, which is going to be located centrally in the middle of that star. The second part of our star includes the radiation zone, which is right on the outside of the core. So it's still internal in the star, but not quite the very center. And the third category here is our convection zone. So that's going to be from the outermost part of our star, and that's going to be the area where heat and light is generating off of, all the way on the outside of our star here. So we're going to go through each of those three types of what makes up a star. So what happens in the core? So we talked about, the core is located centrally in the center of our star here. Well, the core is a very dense and very hot region in the center of that star. And this is where all of our nuclear fusion reactions are happening. They're releasing gamma and X-ray radiation, and it's pretty much like a magma version of what I guess that would be the most closely related to what I could picture what the core of a star would be like. It is very dense. They say it's about 12 times as dense as lead, and it's still in the plasma state. So it's that very viscous plasma. Not quite a liquid, not quite a gas, not quite a solid. It's our plasma state here. And you can see in this image that I've provided on the side here, it shows you what is holding a star together. And so you have our core in the center. You have heat and pressure pushing outward from that core, but you have gravity that's pulling all of the atoms in together. So that's what's kind of holding the star, this big ball of fire and radiation and gamma and X-rays together. So the next zone here is our radiation zone. So what's happening in the radiation zone? Well, this is a little bit less dense than our core. It has approximately the density of water. So just imagine the core being a type of plasma, and then basically like a water type fluid right on the outside in that radiation zone outside of that core. So in this radiation zone, we have energy in the form of gamma rays and X-rays that are coming from the core, and it's being absorbed into that radiation zone and remitted. Then this radiation is slowly diffusing outward, and it's going to probably take millions of years before that radiation finally escapes that radiation zone. So it's moving very slowly over the course of time here. And you can see here the core again, the radiation zone right on the outside of the core. And then the last part here, we're going to be talking about the convection zone. What's happening in this convection zone? So the convection zone is beginning about 7/10 of the way to the surface for this star. And this is where the density of plasma is 1% of the density of water. And in this particular convection zone, or convective zone is another word. I've seen a few different ways of it being pronounced, convective and radiative too. So just keep that in mind. They might be interchangeable. In this convection zone here, at the surface, we're having energy emitted from this zone in the form of three different ways, I guess. So first, it's coming off this energy as visible light, which is why you see a star very bright and glowing. Also, energy is coming off of the star as ultraviolet radiation. And then lastly, there's also energy coming off of the star as infrared radiation. So you have all of this energy coming off of the star. It's coming through the convective zone, so at the surface. So those are our three parts of what makes up a star. But let's talk a little bit about our sun, just because this is the star that we're most familiar with because we see it almost every day. So our sun, our most favorite star, was formed approximately 5 billion years ago. And so scientists believe that our sun has enough sufficient hydrogen in the core of it, because it is also a star. Our sun is a star. So more than enough hydrogen in that core to continue shining and available for use for Earth for another 4 or 5 billion years before it finally burns up and turns into a hard, dark lump of carbon, which is the fate of a lot of stars that have eventually burned out. Okay, so on to our next section here. So our star brightness. So when we talk about stars, obviously when we see them up in the sky, we can see stars that look like they're varying in brightness. If you've ever driven out like in the desert late at night where there's no light pollution anywhere, you might look up at the sky on a clear night and see all these stars that you don't remember seeing, if you're in a big city looking up at the sky. So all that light pollution is really preventing you from seeing all of the really faint, less bright stars. Now, if you're in a city somewhere and you look up at the sky, and even though there's light pollution, you might see the brightest of stars. Well, all of our stars in our sky have different brightness, and they're related to a few different things. So the first thing that brightness of a star can be related to is the amount of light produced by stars. So stars do produce different levels of light. Also the size of the star. So if the star is bigger or smaller, might predict on how bright a star might be. And then lastly, the distance to a particular star. So stars that are farther away might appear as less bright, where stars that are closer, like our sun, for instance, might appear way more bright. Or even our North Star appears very bright as well. So the distance to the star does affect the brightness. And sometimes you'll see that there's a combination of these three things that are responsible for star brightness. So if you have 2 or 3 of these things interacting together, you might see that brightness changes depending on, if the star is very far away but still very large. They might be just as bright as a star that's smaller but closer. So we measure the brightness of stars in a few different ways. So we have a couple terms here. So the first term I want to talk about here is our apparent magnitude. So this is the classification scheme that we have for different levels of brightness that you can see in our stars with your naked eye. So this is just the classification scheme, I guess, that we're using to judge the different levels for the brightness. And so you can see here in this image on the side, this is our apparent magnitude classification scheme. And you can see in this particular image, it goes from negative 28 all the way to 28. Well, originally, the scale only went from 1 to 6. So the brightness values were only running from 1 to 6 originally. The Greek astronomer Hipparchus, he was the original one that created this scale. And he had number 1 as the brightest star and number 6 as the faintest star. But over time, it was determined that there were stars that were brighter than 1 on the scale. And so you can see that and then it went into the negative zone. And you can see that happening here in our sun. So our sun obviously is the closest star to Earth, and it's very, very bright. So that is going to be our brightest star. So on the scale here, it's gone all the way into the negative zone. And right now it falls at approximately negative 27 or so on the apparent magnitude scale. And our Hubble Space Telescope is the farthest away, or the faintest, I guess, not quite the farthest away, but it is the faintest in brightness. So that brightness scale, the Hubble Space Telescope is reading at about 28, but you can't see that with your naked eye. You can only see between 1 and 6 on this scale here, on the apparent magnitude scale. So between 1 and 6 is what you can see with your naked eye. The naked eye limit for farthest away anyway. So that would be 6. So anything fainter than a 6 on the scale, you wouldn't particularly be able to see with the naked eye. You can see one of the Sirius and Polaris are some of the more fainter stars here. Obviously, the sun is the brightest. You can see the full moon falls here around negative 12 or so. Venus at its brightest is very bright, even brighter than Polaris or the North Star, and that runs at probably around negative 4 or so. Also, our next term here is our absolute magnitude. So that is the brightness of a star at the standard distance. So the standard distance in this case is measured at 32.6 light years. So that's kind of the standard that they're using in order to measure that brightness, so that way all stars are on a level playing field. And we're not necessarily using distance to determine the brightness of stars here. We're using the brightness at this standard distance when we're looking at absolute magnitude anyway. Okay, so we're moving on here to star temperature. So obviously we know stars are bright, stars are hot. So when we talk about temperature, have you ever noticed that when you look up at the stars, they might appear a slightly different color? You might see some that are more reddish or bluish or greenish or yellow. And they range from all different colors. And it turns out that colors are the result of different temperatures of stars. So depending on what color you can see these stars falling at, helps us to determine how hot these stars might be. So some of them might be a bit cooler, obviously. Some of them might be a lot hotter, depending on what sort of situation we're dealing with here, what kind of gases, and that sort of thing. Okay, so here you can see that originally star temperatures were classified by color to determine temperature, right? Obviously, based on 16 categories. So according to the strength of the hydrogen line spectra. So there were 16 categories originally looking at color to help determine temperature. And in this category, it's starting at the letter A and going all the way 16 letters down the alphabet to whatever is the 16th letter. A was the strongest in line here when it came to looking at the heat and the color looking at temperature, and B was slightly weaker, and then C was even weaker than B, and D was even weaker than that. But now we're using a sequence that encompasses 7 different classifications. And so those range from the hottest to the coolest, and they're still based on a lettering system in the alphabet, but instead of going A, B, C, D, E, F, G, or whatever, now they have them based on certain letters. So the letters here you can see in bold in my PowerPoint here are O, B, A, F, G, K, and M. So those are our 7 letters that we're working with. And in this particular case, O is our hottest in our sequence, and M is our coolest in the sequence. And so in this nice little graph that I provided on the side here, you can see the classes on the left-hand side of the table, and you can see the temperature in which they fall for that particular class, and then the color that they appear to be. And this includes conventional color and apparent color. And this is just partially due to it's hard to determine the colors based on what you see with the naked eye. So what it might appear in the sky is your apparent color, where your conventional color is more of like what it would be more conventionally known as. So let's go through and just look at a few of them here. So our class O, remember O is our hottest. So that is falling at greater than or equal to 33,000 kelvins. And so this is going to be our blue stars. So our blue stars are going to be our hottest stars, and they're classified as O's. Next in line, we have our B class, which is between 10 and 30,000 kelvins, and that's going to be somewhere between blue to blue-white, somewhere bluish blue-white. And so that falls right after our O. We have our A class, which is between 7,500 to 10,000 kelvins here. And those are going to fall as what appear to be our white or white to blue. So it's going to be mostly whitish in coloration here. Our F class is 6,000 to 7,500 kelvins. That's going to be our yellowish white or white. Apparent in a what we see with the naked eye is going to be more white, which is a lot of your standard stars here. Our G class is going to be 5,200 to 6,000 kelvins. That's going to be yellow stars or yellowish white. You know, a lot of stars in the sky look yellow or yellowish white, so you're going to see a lot of them falling in the middle of the scale here. Our K classification is going to be 3,400 to 5,200 kelvins, so we're getting a lot cooler. These are going to appear as orange or yellow-orange. And then our last class is going to be at our M's, which is going to be less than or equal to 3,700 kelvins. And those are going to appear red or an orange-red. Now this classification sequence makes a lot of sense, because if you think about it, just think about if you have a campfire. Like when you're, out camping or somewheres. But when you have the fire and you're looking into the fire, the hottest part, if you're roasting marshmallows, is going to be that blue section. That's going to be your hottest part of your campfire, and it's going to appear blue. So it appears blue and it's the hottest part. So it makes sense because that's how it's classified on the star scale here. But also if you look at the campfire and you see the yellow flames or the red flames, that's not going to be quite as hot. On the outside of your campfire, where you see the orange and the reds, as compared to the blue section. So it's a little bit cooler in temperature, but it's it really varies depending on the color scheme here. So they have done a really good job with classifying the stars, and something you would think of as like a campfire. So that's kind of like the analogy I've been using to kind of try to remember, what's the hottest and what is the coolest. When I think about a campfire, the blue is the hottest and the orange or the red is the coolest. Same thing with stars. So, all right, so I believe this is all I have today for my presentation for my lecture portion. Hopefully that didn't go too long. I'm going to be putting a few other lectures up really soon here shortly. Now, we do have an extra week to cover in our module series because we had a second week of spring break. And so I might be kind of, I haven't decided yet, but I might be making this a little bit more expedited in presentation, so that way I can squeeze in enough of the lecture series PowerPoints recordings here for the next modules that are going in, because we only have a limited number of weeks and we have one extra module compared to the number of weeks we have, if that makes sense. So I might only be doing 2 or 3 or shorter versions of our module here, so that way we can squeeze in the extra module. So that's just a heads up for you guys, just so that you're aware, and I'll follow up too on email and Cobra, just so everybody knows what's going on. So, all right, until next time.